For the piping, we're going to just kind of go over drawing a flow sheet with a pipe and feed and product. Just look at the pipe, what exactly the pipe does, how it interacts with, in a simulation, times that you might use a pipe. We're expanding the pipe from just a single pipe unit operation to multiple pipes, a network, how that works, how that interacts, balances, flow in a network. We use a pump as well to kind of show the difference between using pipe segments in a scenario where they mix flow together and where they split flow up in a network. If we've got some time, we'll look at some additional examples beyond that, and that will conclude this topic. So for the simulation, to start, we're just going to use a pipe with a feed and a product. Connect them via streams. We're going to have just water going through the system. We'll put water as our component. Click OK on the wizard. This is ideal vapor pressure and SRK. For the example of what we're doing, just kind of balancing and just water through pipe, that this works fine. You don't have to get too fancy here. So now we have our component set, our flow sheet drawn. We just need to specify our stream. Let's just say there's 100-degree water, 50 pounds. I'm going to want 500 gallons per minute. To get 500 gallons per minute, we can change this to weight fraction 1. If the component unit is a dimensionless number, we can change the total flow unit also to be whatever we'd like it to be. We're going to use standard liquid GPM. If the component unit has dimensions, then you can't change the total flow unit and it just totals it up as we've seen before. We'll put in 500 gallons per minute. Okay. So now we have 500 gallons per minute flowing into this pipe. This is what the pipe dialog screens look like. Again, paying attention to the green, we have a method. Do you want two-phase flow, single-phase flow, so on and so forth. You even have our user added if you've got other ways of calculating that you've got your own. Sizing options. Do you want to do it in rating? Basically, we fix the size, and then CHEMCAD does a pressure drop calculation to figure out the pressure, speed, all that stuff, the velocity through the pipe. Or do we want to design it? We can do a design of this and have it calculate the diameter, giving a design criteria. For options 4 and 5, we can do some back calculation. We're going to use option 5 a little bit later. And if we want to design it based just on velocity, we can do that too. For right now, we're going to do it in rating, but I want to show you that if we did like a design, you can kind of see some of these greens change color. Diameter doesn't matter anymore. What you input, because diameter is going to be calculated by CHEMCAD. So it's now grayed out and no longer green. The only thing you have to put in is length. We change back to rating, which is what we're going to use for this. It goes back to green, and we have to take that as a user input. We'll say 6 inches, and we'll say 600 feet long. If you want this in some other format, you can press the F6 button, and it brings up the calculator. and we can do calculations and conversions that way too. But we did change it to inches, oftentimes the diameter, sometimes in feet, so you want to calculate it back. This is taken as an inner diameter. It's important for the calculations. If you specify a schedule, schedule 40, for example, then it will look up the chart and see a 6-inch pipe for schedule 40 has an inner diameter of something different than exactly 6 inches. We can use the help button and we can check this. We look at the pipe schedules for schedule 40, size 6 inches. It's actually 6.065 will be the number used, only if you put in the schedule. If you leave the schedule blank, which I am doing, it will just take 6 inches as the actual number. So for rating mode, that's all you have to put in, those 2 items. We can put more in. There are more things to enter if you want to do a more detailed information. The number of segments for this for this case, means how many times we're going to break up the pipe into different smaller groupings and do a calculation on it. For example, if we did 10 segments, each segment at 60 feet long would be, it would be at 600 feet would be 60 feet. So every 60 or so feet we do calculations. So you can kind of see a breakdown of composition, two-phase flow, single-phase and stuff, where along the pipe and things like that, if you want to break it up into segments for calculation. Optional pipe case studies, we can do that. Let's do 4 and 8. This is for rating mode. We'll say, all right, do the calculations at 6, but also do the calculations and give me some feedback on what it would be if we used a 4-inch pipe or if we also used an 8-inch pipe. And we'll see the results in a second if we use that. Properties. These are just physical properties of the fluid flowing through the pipe. The checkbox means use these fluids. Don't use the fluids that the fluid properties, I should say. Don't use the properties that CHEMCAD calculates for the stream itself. You can override, and in this particular instance, use these bulk properties. Anything that gets calculated gets reported here, including additional case studies, pressure drop and things, and velocities. CHEMCAD follows the crane method for adding additional length for pressure drop. So if we add in some gate valves or butterfly valves, fittings as well, if we have elbows, standard 90, 45s, those sort of things, whatever the equivalent length would be, as determined via the crane method, would be added into the pipe, and that would be the additional pressure drop because of it. The pipe unit operation can also do heat transfer. In the normal default mode, it's just adiabatic. But we can do isothermal as well as heat transfer to ambient. If we do heat transfer to ambient, we've got water, air, soil, or custom if we want to put on insulation around a pipe, that sort of thing. If it's buried in the ground, we're not going to worry about the heat transfer for today's purposes, but just showing you all of the screens available and options available for the pipe. If we leave it as we've got it specified, click OK, and run the pipe. We know we have 50 pounds coming in, we have 45.6 pounds coming out. That's the pressure drop that we've got across this. We can double click and see calculated results. That's our pressure drop. And there's our velocity we're looking at for the fluid flowing through the pipe. Additionally, we did a case study at 4 inches. There's our pressure drop if we used 4-inch pipe, as well as our velocity, and pressure drop at 8 inches. That would be our pressure drop and velocity for 8 inches. So anytime you want to use or calculate the pressure drop in CHEMCAD between 2 points, you need to use pipe. That we've just saw how you would set it up in a rating mode. Everything that we've seen up to this point, we've used a stream to connect one unit operation to the next unit operation. That makes an assumption that the fluid and composition and properties coming out of that unit operation do not change at all before they enter the next unit operation. Under most circumstances, that assumption is probably valid. If you've got unit operations close enough to each other, you're not necessarily worried about a great pressure drop. It's very minimal. You don't have to add additional unit operations everywhere to account for it all, because it would make the simulation much bigger to have all the additional unit operations. But there are times when unit operations are far enough away from each other that you need to take this into account. The pipe would be the exact unit operation that you would use for long runs, big distances, that sort of thing. Additionally, if you've got just a network of piping where you've got multiple streams that are coming and flowing together into a larger pipe or a larger branch network, and that flows in and keeps flowing that way, mixing together and always coming in and combining or dividing, splitting up, say you're cooling water around your plant. You also may have something like a flare header network that you've got multiple streams coming in. You may want to just do an analysis of just the piping. That CHEMCAD can do as well. It's a little bit different than just looking at the rating case like we've done, where we're just looking at a single pipe. We need to add multiple pipes. So we'll add a second one here. A second feed. Use this scenario where we have two different flows coming down 2 different pipes, and they mix together before going into another combined branch. So we want the mixer. Let's reroute that up top. And we combine them all with streams. For this one, we'll put in 100 degrees, 50 pounds. Change it to a fraction of, a fraction of 1. And also 500 pounds. We're also going to leave this in rating mode. The diameter will also be 6 inches. We're only going to run it for 250 feet. That is everything we need to run, to specify that is, in order to run and do calculations. Run all. See, this hasn't changed any. That's still 45.6 pounds pressure out through that pipe. This one's a shorter run, so you'd expect a little higher pressure, a little less pressure drop. Oops, something wrong here. Oh. Let's do that again. I guess I goofed when I put in the total flow of 500 gallons per minute. Okay, there we go. Okay, so like I said, We'd expect a little higher pressure out here, a little less pressure drop because it only has a 250-foot run of piping, and that's what we see. When we come up to this mixer then, we've got 45.6 pounds out. The reason that we've got 45.6 pounds out is when you reach a mixer, CHEMCAD by default automatically puts the outlet pressure from the mixer as the lowest pressure that is entering the mixer. Since this was the lowest pressure at 45.6, 45.6 will be the outlet pressure. In reality, this does not happen. If you've got two pipe flows combining, they will have the same pressure in both of these two spots coming into this joint. They will balance pressure dropped across both lines in order to do so. In order to do that, something has to change from how we have it. We have not specified something that is actual reality. If we had it set up like it was doing, because this pressure is higher than this flow, you would actually see some of this flow going into this branch. So how do we change this? Well, we can use a controller, which we've seen a little bit of already. And just, let's say, stream 4, and we'll go through the logic in just a second as I get set up. Total mass rate. Until stream 5. Pressure. Stream 6. Pressure. Missed that one. Okay, so what this is telling us, because these two pressures do not balance, we either have incorrect flows on one of these two streams, or we have incorrect starting pressures on one of these two streams. We don't necessarily know which. But we know if both of them are at 50 pounds and both of them are at 500 gallons per minute, this is not what will come out. I mean, this won't be balanced. So we'll make the assumption that we know the pressure starting, and we know one of them's at 500 pounds, but we don't necessarily know the other one is at 500 pounds. So we're going to use this controller to adjust the flow rate until these two streams balance. The pressures on these two streams are balanced. And it did not want to find an answer. That is the fun of working with controllers. We can reset things and we can have it work and play with this if we want to, but that's basically how you would set it up. Are not necessarily the best way to go about solving this particular problem. More or less how you'd set it up, I might have something specified incorrectly here, but the better way to do that would be with nodes. If you had multiple, more than just one, these two feeds, you would need another controller. If you had different things that you were going to try to vary, you would need another controller as well. You can only control one particular variable. The more the controllers you have on a flow sheet, the harder it is to solve. The more complex it is, the tougher all in all it is. Chemstations came up with a different way of solving this when we use a unit operation called a node. A node will, the whole thing, controllers do basically the same thing that we're trying to do right now. Is balance the flows through here. Balance the pressure drops through these two lines. Balance the flow rates so that the pressures are balanced. In order to do that, we need to add the nodes into the system that we're using. First, we don't need this controller. Second, we need to insert a node here. And here as well. After I get this drawn, and we swap out the mixer. Yes, that's fine. Okay. So a node is a point in a flow network system that will be used to balance the pressures, as well as working with flow scaling unit operations to balance the flows as well. You need to put a node before and after any flow scaling unit operation. A flow scaling unit operation can be a pipe, like we have, a pump, a compressor, an expander, as well as a control valve. But the unit operations don't necessarily need to be flow scaling unit operations. We have to change the mode that this pipe is working in order for it to be a flow scaling unit operation. We'll get to that in just a second. First, we'll start with what a node looks like. We've got modes, variable pressure or fixed pressure, and then we got flow rate options. We can change it to use stream rate, fix the stream rate, or flow set by unit operation. Those are our options. We'll come back in and start specifying in a second once we kind of understand the logic to it. So this is going to specify a pressure and figure out a flow rate through, calculate a flow rate. We have to change this if we're using it in a flow scale operation to mode 5, which I mentioned earlier that we'll be moving to. Now that we're in mode 5, we're going to be given the pressure, and from the pressures we're going to calculate flow rate. Then we have another node that's going to be given the flow rate, and it's going to calculate the pressure. We have to change this one to mode 5 also. So because we have these two now as flow scaling unit operations, because they are in mode 5, or sizing option 5, I'm sorry, we have to have a node before and after them. Now, these two, like I said, these nodes will be given the flow rates, and they will calculate a pressure. Pressure will be given to these unit operations. Unit operations will take the pressures in and out, calculate the flow rates, and so on and so forth until this all balances. And it will all be solved simultaneously. Previously, ChemCAD has been working as a sequential solver. First, unit op 1, then unit op 2, then unit op 3, and on down the line until, if we got to recycle, it goes back around to the beginning until it all balances. Now we're going to solve everything simultaneously. That means we can actually specify endpoints if we need, middle points if we know them, and we can calculate backwards if we need. In order to solve everything simultaneously, we need to set up some degrees of freedom boundaries. We need to specify so many things in order to satisfy the equations, but we can't overspecify things. We need to fix exactly the number of things, items, I'll tell you in a second which items can be fixed, as there are a number of inlets and outlets into a network. In this case, we have 3 inlets and outlets. 2 inlets, 1 outlet, giving 3 items that we can fix. The items that can be fixed are fixed in the nodes, and they are either pressure, which you can fix anywhere, or flow rate, which you can fix at either a feed arrow or a product arrow. You can't fix flow in the middle of a network, but you can fix pressure in the middle of a network. Back to our original problem, we stated that we knew things were coming in at 50 pounds pressure. So that's 1 degree we have set, 1 variable we've fixed. We also stated we knew that we had 500 gallons per minute flowing through. So that's 2 items we have set. Because it's flowing out into a flow scaling unit operation, this is always going to be in flow set by UnitOp. We can only fix 1 more item, and we'll do it in this mode, or this node. And as we did the original problem, we'll say we'll fix this pressure. We are going to free the inlet stream, which means it's not constrained at all. Essentially, it's going to act like the controller was going to set up where it would scale the flow up or down depending on what it needs to in order to satisfy and balance the situation. And then flow set by UnitOp, because the flow out of the node is going to a flow scaling unit operation. In this node, we are letting it be variable pressure. We're not fixing it. We don't know what the pressure is going to be. The flow coming into it is coming from a flow scaling unit operation, so therefore it's flow set by UnitOp for both of them. And because we have all of our degrees of freedom fixed, we're just going to free the outlet stream. That means it's going to be whatever it is that comes in order to balance it, that's what's going to go out. We run this. We've got 496 standard liquid gallons per minute. If we look on the view properties, that is .500 actual volume gallons per minute. We've just adjusted from excuse me, from standard to the pressure that we're at. And down at the bottom, we've got 781 gallons per minute, standard liquids gallons per minute coming through. So that is what is actually needed in order to balance this flow and have both branches come out at 45.6 to have the flow rate, the pressures balance through both branches. And therefore the pressure at string 3 coming out balanced of the whole system. Well, let's change up the problem a little bit. Let's say we know 1,000 gallons comes through. That's why we set 500 in each branch. We're not really sure how much is going through each branch, but we know 1,000 comes out. And we know it starts at 50 pounds. In that case, we leave this at fixed pressure 50 and free inlet stream. In this case, we still leave that at fixed pressure at 50, but now we don't put 500 here, remove it, and we put free inlet stream. And now we fix the outlet pressure, the outlet flow rate to 1,000 gallons per minute. We can fix the flow rate here because this is going to a product arrow. If this was going to some other part of the network, we could not do so. We run it, it's finished. Take a peek at things. Now we see, oops, that's not the one I wanted, 384 standard liquid gallons per minute are coming through. Or if we look at just the liquid, actual, 387 is what comes through the upper branch, and we have 607 through the lower branch in order to reach the 1,000. Now that's 992 because, again, that's standard. It's 1,000 actual gallons per minute as opposed to standard liquid gallons per minute. So that's how we can do a balance if that's the criteria we know. Again, it doesn't really matter which ones we set. We just have to set 3 of them. And we have to set it such that it solves the problem we're trying to solve. What pieces of data do we know? And what pieces of data do we not know? What do we want to solve for? That's using it as a mixer. We can also use this as a divider. Just going to Control C, standard Windows copy, and Control V. Paste everything exactly as it's connected and everything, and we pull it down here. I'm going to add a pump. Another pipe. That should be enough for right now. Let's fit this. Before I do that. Okay. So now, since this is not going to a feed or a product arrow anymore, we can't specify the flow right here like we had specified. We can change this back, though, so we know that we've got properties. Whoops. This is 384 standard liquid gallons per minute coming through, which is properties 387, I believe it was. So 387, let's call it 388 coming through this branch. So if we solve that, we can set this for volume rate, 388. We change this to free outlet stream like it was before. And since we fix this at 388, that's the balance. We know that this one will be the 607 or so that it is right now. So we've solved and been able to specify this stream here and still come up with 1,000 gallons per minute here. We need to move, beef things back up to 50 or so pounds coming out. So let's put this up to 50. We're going to do another pipe. In this case, we're in rating mode because we're not flow scaling it. We don't have nodes in this part of the network. 6 inches, 750 feet. And we run it. We'll get more pressure drop through here. $20 pounds pressure drop. Our pressure out is 29. We wanted 50, so we know we have to increase the pressure here. It's pretty straightforward math. We could just add the pressure drop into it, and we would be able to get it to the right amount. We're pretty close there. If you wanted to get it real accurate, is also in order to have it solve, say you change things here and automatically solve, the way we've got to set it up now, you'd have to use a controller. Adjust the pressure in this pump until the pressure through this flow rate, until the pressure out of this pipe, and based on the flow rate, is 50 pounds. Similar to what we saw up here. but again, we don't really want to use controllers. Also, what happens if we get in the scenario where instead of just a single branch, we've got some flow that comes off a second branch, or maybe a third branch, or maybe a fourth branch? It gets very convoluted and very hard to solve that with controllers. So again, we turn to the nodes to do so. If we take this as an upper branch, we insert a node here, insert unit, okay. Since we're going to use these pipes in flow scaling, we need to start with something, a node before them and nodes after them. So we have to add some nodes in here as well. And one more. Okay, so we've got it drawn. Because this pump is not flow scaling, we're not using it in a flow scaling mode, we could, if we used one of these options here with the performance curves, we just want it simply to increase the pressure. That actually means we have two different small flow networks. We have this one, which we have set, and we're not going to adjust or change at all at this point. And we have this one. So we have one that mixes, and we have one that divides flow. First, we have to make sure our pipes are in flow scaling mode, sizing option 5. That is 6 and 750 feet. We can leave that. That's fine. Let's change this one from to mode 5, which it is. We'll call this one 4 inches and 150 feet. It's a shorter little pipe. Okay, at this point, we don't know the pressure out, so it's going to have to be variable pressure. Flow set by UnitOp actually is going to be use current stream rate. Whatever's coming through, that's what we're going to use. We're going to fix the pressure on the end, and again, we want 50 pounds out. Because we use the current stream rate, the 1,000 gallons per minute coming in, that fixed one thing. We check here, we have 50 pounds and 555 gallons per minute. We have 50 pounds and 438 gallons per minute. So we've solved it. Let's say we don't necessarily know if there's 50 pounds coming through. Maybe it's only 45 pounds that needs to come out here. We can change that to 45. Rerun this. It will rebalance everything. We're at 45 now, and now we've increased the flow because we don't have as big a pressure drop. And always it adjusts the pressure outlet from the pipe or from the pump based on what we need. Let's say we want to just free this inlet stream. It still will use basically whatever's coming through. But by changing that, and we'll see in a second, I've changed the degrees of freedom. Now I can actually specify one more thing someplace. And I'm going to change the pressure here. I'm going to fix an internal pressure and just say, I know I need 60 pounds at that point for some reason. Just hypothetical. So now my 3 settings, because I have 3 degrees I need to set here, one for the flow coming into the network, 2 more for the flows going out of the network, and I have set pressures at each of them. Has worked 60, and as you could imagine, we need 60 pounds out of the pump in this regard. We've increased the flow some, which back calculated the flow, but we've fixed that. And we still have 50 pounds coming out and 45 pounds coming out. So it just depends on what criteria you need to solve. You can use flow networks and you can use nodes to solve them. If you're looking at multiple pipes branching where the flows go from one pipe go into other pipes, split off of different pipes, things like that. We got a couple of examples we can go through. To look at just some other ways that we've done with pipes. So now that I say that, I can close it and look at a couple other pipe scenarios, simulations. Again, back to the examples folder directory. This is, again, simulations that you have available to you. If we look at example 3, kind of similar setup. We've got a pump, and then in this case, though, we've got pipes. We have a control valve that's going to be dropping pressure here and scaling the flow, basically a restriction in the line. We've got it going through 2 different branches through 2 different heat exchangers. If you noticed here, we have a node, pipe, then a heat exchanger before we have the next node. I stated that you have to have a node before and after each flow scaling unit operation. Well, we do here. The heat exchanger is not a flow scaling unit operation. It can do a pressure drop, but it's not going to scale the flow in any way, shape, or form with how it's set up in CHEMCAD. So because we have one before this pipe and we have one after this pipe before the next flow scaling unit operation, which is this pipe, we have satisfied the criteria. We could have put the heat exchanger after this node or before this node. It would not have made a difference. But you just have to have a node between this pipe and this pipe somewhere. So that's how that's set up. So we can have flow going through either one of these 2 branches. It combines again and comes out to the same header, which is probably close to atmospheric if this would be for either a cooling water flow or for a flare header network. 20, so close to atmospheric. Another example, one more to show. In this case, we've got a lot of different lines coming in, all going to atmospheric for a relief scenario. We've got 4 different lines that could flow into a relief network. And in different cases, you could turn on or off these valves if they're open, flow going through or not. These are simply on-off valves. They allow flow to go through or not go through. And you can see how if flow is coming through multiple lines, how it starts to affect the back pressure on other lines and things like that. Those can all be done in an analysis with nodes and with the pipe network. Again, just a couple of different examples beyond what we've shown to see how additional uses of the tools. So to summarize, we saw how to set up and specify a pipe and then run it. We kind of expanded that pipe from just being used here and there for pressure drop calculations to be able to balance flow both in mixing and in splitting flow. We used to show that controllers, or at least kind of set up that a controller would be much more painstaking in most regards, especially with multiple pipes and branches. We saw some additional examples on how to do this as well. And that concludes the pipe topic for our CHEMCAD Essentials course. We have about 10 minutes if there are any questions. There is a question that someone has asked, is there a quick way to see what a GPM is? I'm not sure. The question would be actual versus standard GPM. Let's see here. The standard is always going to be what we display here. And in the flow units, if we have this changed to any of these are all at standard STP, GPM. The only quick way that I know of beyond is to view the properties and look at them right next to each other. Standard liquid, standard vapor, actual vapor, volume, standard. In this case, it's volume for feet cube, standard feet cube per hour, volume feet cube per hour. So they're in the same units more or less, but it's the standard versus the actual. If you right-click and choose the properties, they will show those two numbers right next to each other. That's the only way that I know of to do a quick view of them. What we use for standard temperature and pressures can be where is, hold on, bear with me. Format engineering units. Under options and references for the format engineering units, you can change what you want for the default for the reference temperatures for atmospheric as well as for vapor to change what the standard liquid in is. But the only way to see those, the difference between those two would be to view the properties and see them both printed right next to each other. We don't ever put the actual on the quick view.